Today we're going to, after treating Poynting's theorem last class and going over a couple of examples, today we will go to the Maxwell stress tensor. And the Maxwell stress tensor is a super useful concept, and it's another one of those things where we have some kind of an expression, and just like with Poynting's theorem, we started with the energy density. We know that it's E squared plus B squared integrated over space over 8 pi. And then if we just say, hey, what allows this to vary as a function of time, we take a ddt. And then that means we get a ddt of an electric field and a ddt of a magnetic field. And then we insert Maxwell's equations into it, and then we get some kind of an expression that has that tells you what the energy flow is, independent of where the currents actually are. So all you need to know are the fields. So that's a beautiful thing to do. And when we do the Maxwell stress tensor, we'll do something similar. But I'm going to jump over the majority of that derivation because it's kind of long, and otherwise we won't be able to actually use it. The power of the Maxwell stress tensor is that it allows you to calculate the forces on current carrying objects or charges that are moving, or static charges, or mirrors that reflect electromagnetic waves, knowing only what the electric and the magnetic fields are. And it's a beautiful thing, and but it's a little bit hard to read because it involves this thing called a tensor. So it does involve a thing called a tensor because we need something that, when we start talking about force balances, gives you a direction, right? So if we need a direction, then out should come some kind of a vector thing. So we'll need a tensor because otherwise we won't be able to pull out the vector. It does make it a little bit harder to read. So that's why, so we'll go quickly over the setup, how one would derive the form of the Maxwell stress tensor. But then we'll do two examples that are very useful to illustrate the power of it. And then when we do electromagnetic waves, let me see, I think that'll probably be the next class. When we do electromagnetic waves, it's the easiest way to calculate the radiation pressure exerted on a mirror or some kind of an absorbing plate when there's an electromagnetic wave that is incident on that plane. It's very straightforward to do once you know how to manipulate that tensor object to give you a force or a pressure. The Maxwell stress tensor. So Poynting's theorem describes momentum, describes energy conservation. Now let's do momentum conservation. So we start with the Poynting vector. Poynting vector, which is this one we used extensively last class. And then we use the fact that the momentum density follows from energy from the Poynting vector. So the momentum density and we use little g because the book uses it. It's just this Poynting vector divided by c squared. Okay, and now we know that when momentum changes as a function of time, we're talking about forces or pressures or force densities. So we want to look at this object, this dg dt, and it's a vector. and it's basically pressure, if you want to think about it that way. Now, pressure, I wrote it here as a vector because it is directed. It's usually not how we think about it. We usually think of pressure as a as a as a as a scalar. But in this case, because we're going to see what happens when you get a difference in electromagnetic fields, we'll get some kind of a force that has a direction. So therefore, also the pressure must have some kind of a direction. Okay, so so we start by calculating this dg dt, and so we just plug it in. So it's the ddt of 1 over c squared times c over 4 pi e crossed with b. Now, factor these two out, we'll get chain rule and product rule. So the product rule will give one a del TE and a del TB term. And the large part of this derivation goes into pulling these from Maxwell's equations. So this one is pulled from Ampere Maxwell. And this one is pulled from Faraday's law. Okay. Now, like I said, I'm going to skip over the derivation and I'll show you what the end result looks like. So the end result looks as follows. We have a del T of G, but it's the ith component of that vector. And it is equal to minus del I, so that's a d dxi of this expression, which is 1 over 4 pi, and then it's 1/2 e squared plus b squared, and then there's a delta here, delta ij, minus rho ei minus 1 over c, and then here is the j crossed with b, and it's the ith component. Okay, now let's point out some things. Oops, this is the easiest one to see. This is static energy pressure. So, you know, compare this to, let's say you have a Q times E. We know that Q times E gives you a force. So this is not force, but it's force density, because instead of a Q, we have a rho. Okay, so this is electric force density. Okay, now this one looks just like 1 over c I crossed b, sorry, IL crossed b, except it's not I, it is J. So this is magnetic force density. And again, all of those things come in because when we swap in Ampere Maxwell's law, there is and when we swap into Ampere Maxwell and when we swap in Faraday's law, those terms show up. The rho comes from Gauss's law. Anyway, so this is the one to pay attention to. This is what we call Tij, and this is the stress tensor. sometimes called the Maxwell stress tensor. So if you look very carefully at this, you'll see that we have here, therefore, a minus the divergence of this stress tensor. And you see it is a divergence because there's a dot product, because that sum over I is implied. So for instance, compare del I EI, that's the divergence of E, right? So we do have a divergence here, but it's the divergence that takes the derivative along the I direction, but it only is a sum over the I direction, and you still have a term left. And now I see, actually, I made a little mistake here. That's actually not I, that is J. Make sure, fix that. Yeah, that's J, and that's a J. And that's, unfortunately, that's the J, the index, not J, the current density. We use J twice in this expression, unfortunately, cannot be helped. Okay, so this is some kind of a divergence of this mysterious object that we call the Maxwell stress tensor. And then minus that rho EI, and minus the 1 over C J crossed with B, and then the ith component. Okay, so these are electromagnetic force densities, right, together. Oops. Now comes the trick. Why is this expression useful? It is because we can set the left-hand side to 0. So if we want equilibrium, or if we want momentum conservation, which seems reasonable, momentum conservation, then this first term, the divergence of that stress tensor, must be equal to the thing that is underlined in blue. Which means, if they're the same, we don't need to actually explicitly calculate the forces, which would require us to know not just the fields, but also where the currents are and where the charged objects are. We can instead, because it's equal to that divergence of the stress tensor, we can calculate the forces on objects by just taking the divergence of that stress tensor. That's the magic of the Maxwell stress tensor. Okay, so rather than calculating this thing directly, when del Tg I is 0, it is equal to minus del J T I J. So all of the useful stuff comes from the fact that we need to figure out a way to calculate this property, the divergence of that stress tensor with a minus sign, for specific cases. And because, as you can see, that Maxwell stress tensor has in it only, I forgot some terms. The Maxwell stress tensor has in it only electric and magnetic fields. We can calculate the forces on current carrying wires and charged objects without knowing actually where the charges are, how big they are, where the currents are, how big they are, because the currents and the charges are implied by a certain electric and magnetic field configuration. So all we're doing is, once we know that electric and magnetic field configuration, we also know the force on whatever is responsible for creating that field, because Maxwell's equations give you that. Okay, so now let me add the two terms, because those are important. There's a minus EIEJ, and there's a minus BIBJ. Okay. Come on. Okay, so that's the stress tensor. So what does this thing look like? Well, first of all, this is a stress tensor. This is an object that later on we will discover looks a little bit different than regular matrix. When you do linear algebra, usually you sum, you have some kind of a matrix vector product or some kind of a matrix product. We usually have some kind of an implied assumption for whether the first index indicates rows or whether the first index indicates columns. So whenever we write something in matrix form, we should really always be aware of the fact that that first index versus the second index might refer to rows or columns, or vice versa. Fortunately, this thing is symmetric, so we don't have to worry about it. So if you look at that, hopefully you'll see that delta ij is symmetric. That's just an identity matrix, right? It has only ones on a diagonal when I is equal to j. And when you swap in that second term, the EI, EJ, you swap the J for the I, and vice versa, you get the same product. Same thing with that BI, BJ. Okay, so it is a symmetric tensor. Is symmetric, which is important. But it also means that we can just, without paying attention to exactly whether we're talking about rows or columns, we can just draw it like a regular matrix. Okay, so this is 1/2 E squared plus B squared. And this is 1/2 E squared plus B squared. And this is also 1/2 E squared plus B squared. Okay, on the non-diagonal elements, we get things like this. This is an EX, EY minus BX, BY. And then, for instance, here we would have a minus EZ, EY minus BZ, BY. Okay, so that's what this thing looks like. I'm not going to complete these two, but hopefully you see the way this thing looks. So now let's put this thing to work. Let's put it to work. For this, we need to convert this thing from differential version to integral version. Okay, so we're going to do that. So we're going to go put an integral here, and we'll say this is a volume integral of del. It doesn't matter, but let's call it J. Oops. Del I Tij d3x. And now we're going to use that Gauss's theorem, and we'll convert that to a surface integral. Okay, T I j, and this is d squared s I. Okay, so this looks like flux, except this flux has a direction. It's not a scalar thing. So this is like momentum flux. Okay, so there are two famous examples. Let's start with number one. Make a new one. The solenoid. All right, the solenoid's interesting because what we'll do is we'll say, okay, let's start by doing this, put a coordinate system. Okay, X and a Y and a Z. And then we'll draw current carrying loop here, and then there's another one here. You know, these are connected with little wires. And let's say that the current circulates in this manner. So this is the current. Then this would generate a magnetic field in the Z direction. So that's B, which is some Z hat times B, some number. And let's draw also a top view. So X, Y. So we're looking down on it. Oops, let's actually draw this as an actual circle. Surprisingly difficult. Okay, so current goes in this direction. And the magnetic field is pointing at you. So there's B, 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 B. And now we're going to use a Gaussian surface, and we're going to stick this Gaussian surface here. Such that the normal here is NX. The normal here is NY. This is minus NY. And this is minus NX. And we'll need these normals because now we're going to actually calculate the divergence of the stress tensor in this box. But we're not calculating the divergence explicitly. We're using this flux integral, just like when we do Gauss's law in electrostatics. You know, the divergence of E is 4 pi rho. Most of the time, when you do any kind of realistic situation, you don't actually calculate that divergence explicitly. You go to this integral form and you just look at the flux on one side, flux on the other side, and then Q enclosed. So we're doing the same thing here. But instead of looking at the flux on one side, the flux on the other side, we're looking at what happens to the stress tensor on the sides of that box. Okay, so now we need to actually calculate the stress tensor. And these are backwards. Make sure fix that. And then that means that these are also all backwards. This would be Y. Whoop. X and X. Okay. So here we go. So use the Maxwell stress tensor to calculate the pressure on the current carrying wires. Okay, so what is the Maxwell stress tensor for this case? All right, well, let's look at this. We have a Tij 1/4 pi. There's a 1/2 E² plus B². delta ij minus ei ej minus bi bj. Okay, that's the stress tensor. I usually like drawing this in curly braces. Okay, in this case, there is no electric field, so that's easy. We throw this one out, and we throw this one out. Okay, now, B has only a Z component. So let's look at, so B is some B, Z, Z hat. Let's calculate these things. Okay, so let's look at T, XX. So that will be the XX entry for this thing. All right, here we go. 1 over 4 pi. There's a 1/2. Now, when I and j are both x, that delta says it's the delta of xx, so that's 1. So that term survives, and it's b squared. And it is, in fact, the z component of b squared. So correct, this is bz squared because b is z squared. Okay. Now, minus, and now we need to do a bi bj, but when I and j are both x, b is 0. Okay, so there is bi bj. These are both 0. Okay, so the xx component is the xx component is just b squared over 8 pi. Okay, now let's look at the next one. Tyy. We would have identical term here, and we would again get a b squared. And again, that byy disappears. So this is just, again, b squared over 8 pi. Okay. T, zz. Okay, now this is interesting. So we get 1 over 4 pi, 1/2. And then we get b squared. But now we need to subtract bi bj, where both I and j are z, so we actually have minus bz squared. And b squared and bz squared are the same. So this thing is actually minus b squared over 8 pi. So the it's a completely diagonal matrix. So if you want to draw it, it's just b squared over b squared over 8 pi, and it's 1, 1, minus 1. Okay, 0 is here, 0 is there. Okay, now let's go back to our Gaussian green box. What we're looking for is an expression, is an evaluation of what happens to the stress tensor as we are evaluating the different sides here, where they are seeing a difference in the stress tensor. So if you look at this, so let's look at this top one first. So we know that the stress tensor inside of the volume is it's got this b squared over 8 pi, and it's 1, 1, minus 1. But it's the same on the top as it is on the bottom. So then, because the normals are different, but the stress tensors are the same, these things will cancel. So they cancel. These two cancel. So the only thing that we need to worry about is the fact that the left side of this box is in the magnetic field, so therefore the stress tensor is not zero. And the right side of this box is not in the field because outside of the infinite solenoid, the magnetic field is zero. And because the stress tensor changes, we can calculate what is responsible for that change, and it would be that current. Okay, we calculate the force on that current carrying wire. Okay, so let's now write down what we mean by this. So the ith component of that force is minus the integral of T ij d2s j, and we can also write this as the nj d2, oops, nj d2s. So this is a surface element with a normal pointing in the jth direction. All right. So the left face and the right face of this box, the normal is pointing in the, let's see, the normal is pointing in the y direction. Okay, and because the normal is pointing in the y direction, we need to look at the stress tensor, the y component. Okay, so J is the y component, and because the is diagonal, we only need to worry about the T-Y-Y component. Okay, so the force on the y component is going to be minus the integral of T y y d d2s y. So that's the only one we need to worry about. Okay. Now, the thing we need to worry about also is the fact that when we're looking at this green box here, the stress tensor is non-zero on the left face. Okay, so Tyy is non-zero on the left face, but Tyy on the right face is zero. So when we calculate this integral of this flux, we need to pay attention. We're talking about the left face of the box. And for that left face of the box, the normal is pointing in the minus y direction. Okay, so the normal here picks up a minus sign. So we fix this because normal is in minus y hat direction. Okay. All right, well, what's the number? Okay, Tyy, we'll look it up. Tyy is this guy. It's just 1 times b squared over 8 pi. All right, here we go. So we get b squared over 8 pi. And we still integrate that over the entire face. So times A, this is the surface area of one of those faces. Well, let me make that green. That's the surface area of this face on the left. Something I did not mention explicitly is that when you look at this green box, we're making sure that the green box is small enough such that we don't really need to worry too much about the fact that this wire is curving. So it's kind of like an infinitesimally small box. So keep it small enough so we can assume that that wire is like straight. Okay. So let me make sure. Box, small box, such that that I is just going straight up. Okay. So what do we get? In the end, we get a force in the y direction that is proportional to the area. So therefore, the pressure is the force over the area. It's just b squared over 8 pi. Okay, so this solenoid, by virtue of keeping a magnetic field contained inside of it, experiences a gradient when you go from the inside to the outside. And because of that, there's an outward pressure on the windings of that solenoid. And in fact, if you make a solenoid and you make the field really, really strong, this thing will unwind itself and will become a straight line because it cannot contain that magnetic pressure. And in fact, this is the same pressure that you would find if you were to calculate the Lorentz force. So let's just do a check. So let's say if we have a current in this direction and we have a magnetic field in this direction, what would be the direction of the Lorentz force on this current carrying wire? Use your right hand rule. The Lorentz force will be to the right. The Lorentz force would be to the right, and it would be exactly b squared over 8 pi. And we get the direction. Yeah, do your right hand and your left hand rules. You get the direction and the magnitude. We didn't actually even need to consider the fact that there was a current carrying wire because it's implied by that balance in the Maxwell stress tensor. So we don't even need to know what I is in order to calculate how big the force is on that solenoid. I hope you realize how powerful that is. So by just knowing that the field is like this, we know automatically there's a force on it. Example 2. The capacitor. Oops. Okay, so let's say we have a situation where we have a parallel plate capacitor. We again are assuming, ideal parallel plate capacitors makes life easy. That's X, that's Y, and that's Z. And now we're going to put a parallel plate capacitor, we're going to put it like this. And then we're going to make the top one negative. Oh, that's negative. And then the bottom one, we're going to make it positive. Now, this is the electric field. And again, we're assuming that it's uniform and it's in the Z direction only. E is uniform. So E is EZ, Z hat, if you want to write it this way. Okay. Now we're going to do the same thing. We're going to say the field is contained to the region in between the plates. So that means that the stress tensor is something finite inside and it's 0 outside. So we're going to take a Gaussian box and we're going to put it over the thing and we'll do the same thing. Now, anybody want to take a guess what direction the force is going to be on the plates? are these plates being pushed apart or are they pulled together? Think about that for a minute. Okay, so because opposites attract, they should be pulled together. Oops, pulled together. Opposites attract. All right, now let's do this with the stress tensor and convince ourselves that it's the right answer. All right, here we go. T, xx. It's going to be 1 over 4 pi, and it's going to be 1/2 EZ squared minus EX, which is 0, so 0. So we just get E squared over 8 pi. Okay, TYY. Same thing, we get E squared for 8 pi. Okay, and now TZZ. We get, okay, 1 over 4 pi, and we have 1/2 EZ squared minus, and now those two EZ squareds are not 0, so we have this EZ, so that's EZ squared. So we get minus E squared over 8 pi. Okay. All right, so let's write it in matrix form. So it's E squared over 8 pi, 1, 1, minus 1. Okay, now this is NB identical to the solenoid, right? Except when you swap the E and the B, right? Now this is surprising because we know that the solenoid was being pushed apart, and we know that these plates will be pulled together. So how is it that when the stress tensor looks the same, is identical, that we can still get such a completely different answer? And it has to do with the geometry of this charge configuration that is responsible for the field. So as we will see, we will need a Gaussian box that we need to place on a different spot than when we have the solenoid, because electricity and magnetism are different, right? You can't generate a field this way unless you place the plates to the top and to the bottom. If you want to create a magnetic field in that direction, you need to take a solenoid and make turns, and therefore your Gaussian box is going to sit on the side rather than on one of the top or the bottoms. And because the Gaussian box goes in a different spot, it has a different geometry and therefore experiences a different gradient, and therefore the force is going to be completely different. Okay, so you'll see. Okay, so let's pick the let's pick the box. Okay, so we'll put one of these boxes, we'll put it here. Okay. Put one of these boxes here. So box on the top, and then below. Okay. So the normal in this case that we need to worry about is the normal in the z direction. Okay, so this is the normal in the z direction, because the normals in x and y see the same field. So because they see the same field, you know, the field on the left side and the field on the right side is the same. So if the field is the same, but the normal is different, that means that the contribution due to that stress tensor gradient is going to be 0. Okay, so the sides cancel because E is the same. and n flips. Right, so then when you do your counting, you see you have a gradient. You have a field tensor on the left, field tensor on the right, same number. So therefore, because the normals are pointing in the other direction, you need to worry about it. Now, the only one that experiences some kind of a change in the field tensor is the face on the z with the normal in the z direction. So the top plate of this Gaussian box has a normal that's pointing in the z direction, but it is in the region where the electric field is 0. So T is 0 here, but T here is not 0. So that's what we need to worry about. All right, so let's write down the force. Okay, the force in the z direction would be minus the integral of T z d2 sz. Okay. Now, because only the bottom part is contributing to this integral, the normal on the bottom is pointing in the minus z direction. So we need to pick up a minus here because only the bottom part. For which it's minus, sorry, n is in the minus z hat direction. Okay, so that's why we pick up a minus sign here. And then we'll do that. I'm being a little sloppy, but we'll see in a little bit. Okay, so we'll get minus t zz, sorry, plus times the surface area of that green box. So let me fix this. Yeah, so that's why it flips signs. Okay, now what is TZZ? Well, TZZ happens to be negative. All right, so it's minus e squared times a over 8 pi. Okay, so it's down. Right? Force is down. Because, opposites attract. That's always nice when the universe works in this way. The really, really long way of finding that opposites attract. Okay, so now that we have this this thing calculated, we can do something similar as what we're doing when we do Gauss's law in elementary introduction to electromagnetism. Let's say we make the Gaussian box this size, right? We make it go all the way through. For this red box, the top of that box is in a place where the E field is 0, and the bottom of that box is in an E field where in a region of space where the E field is again 0, which means that there's no force, there's no net force on all this stuff that's in the red box. So net force is 0. Which means that now that we have that the force on the top is down, that means the force on the bottom needs to be up. And it comes right out of this Gaussian box and the stress tensor. Okay, so therefore the force on the bottom plate is up. Yay, that works. All right, now Here's a really cool puzzle, and it's a puzzle that is actually part of it. I posted it somewhere in one of the homeworks. It's kind of cool. And it's this configuration where this is a charged object with a gap, and the gap has a taper. So there's an electric field here. I forgot what the direction is. And you can use the Maxwell stress tensor to calculate the force between these two conductors or charged objects. It's called charged objects. These two charged objects. Right, so this is an electric field. Let's say this is positive, it's negative. And the beautiful thing about it is that this is a weird configuration, right? We don't really know what the charge configuration will do. Like, you know, I don't know what's happening here. Like, what's happening with Q here? Do we get a weird, I don't know, do we get like an accumulation of charge? So the beautiful thing is that because of this power of Maxwell stress tensor in integral form, you can calculate the force between these two objects without knowing the charge distribution. And that's the power of the Maxwell stress tensor.